Hi, I am Dr. Josh Butler, faculty member at NTID's Information and Computing Studies Department. Today, I want to share with you a project that combines my passion for electrical engineering and chess. I've always been fascinated by the world of electrical engineering, and I wanted to expand my skill set by creating a customized controller that incorporates different features, such as I/O expander, ambient light sensors, magnetic sensors, and addressable LEDs. To make the project even more exciting, I decided to combine it with my love for chess. The result? A chessboard with LED lights that indicate the moves. The board uses various sensors to detect the position of the pieces, and the LEDs light up to show the player's move. It's a fun and interactive way to play chess that also showcases the potential of electrical engineering. At NTID, we're committed to empowering our students to explore their passions and pursue their interests. Whether it's through DIY projects like this one or through traditional coursework, we're dedicated to providing our students with the tools they need to succeed. Thank you for joining me today, and if you have any suggestions for improvement to this project, feel free to share with me. And as always, happy tinkering! To make my chessboard project a reality, I wanted it to have several key features that would enhance the playing experience. These features included the ability to detect the position of chess pieces using Hall sensors in every square of the chessboard. These sensors can detect the presence of a magnetic field, allowing the microcontroller to determine which piece is where on the board. Addressable RGB LEDs that light up on the chessboard to show possible legal moves for the piece that was lifted off the board. This feature makes it easier for players to see their options and plan their next moves. A microcontroller capable of running MicroPython with access to Wi-Fi internet. This allows the chessboard to interact with a chess engine, enabling players to get real-time CPU moves. Since the board has 64 squares, the microcontroller did not have enough I/O pins to detect the state of each square, whether a piece is in the square or not. To solve this problem, I used I/O expander chips that enable me to pull 64 squares using only 2 wires to get the data for the program to work out the positions of all pieces. Finally, since LEDs are being used on the board, I wanted to ensure that the LEDs don't get too bright in a dark room. To accomplish this, I incorporated an ambient light sensor that measures the brightness of the environment and adjusts the LED brightness accordingly. By incorporating these features, my chessboard project became a true testament to the possibilities of electrical engineering and its application to the world of gaming. Let's take a closer look at the schematic for my custom chessboard project. This schematic combines the controller and the chessboard into one integrated system, featuring several key components: a USB-C connector for communicating with the microcontroller, programming, and supplying power to the board, a USB to serial chip for programming and console output, a step-down regulator to step down the power from 5 volts to 3.3 volts, a micro SD card to store the move history for each game, a chess clock display for each player, a touchscreen display to allow user interaction with the controller, a multiplexer to enable the use of 2 chess clock displays sharing the same address. The main microcontroller, S32, was selected for its Wi-Fi capability. Next, we have the addressable RGB LED matrix for the 64 squares of the chessboard. To ensure that the signal was properly shifted from 3.3 volts to 5 volts, I used a logic level shifter. To detect the state of each square, I used I/O expanders. Each expander can handle up to 16 I/O signals, and 4 were needed for the 64 squares. Each one has an assigned address for I2C communication with the controller. I also included 1 extra expander for tactile buttons. Finally, I incorporated Hall sensors, 1 for each square, for a total of 64. These sensors detect the magnetic fields of the chess pieces, allowing the microcontroller to determine their position on the board. By combining these components in a carefully designed schematic, I was able to create a custom chessboard that pushes the boundaries of what's possible with electrical engineering. Here's where the rubber meets the road. The initial printed circuit board layout is the culmination of months of design and planning. Every component was carefully chosen to ensure maximum performance and functionality. At the heart of the board is the ESP32 microcontroller. This powerful chip provides the processing power needed to handle the complex logic of the chess game, including tracking the movement of the pieces and determining the legality of each move. The board features a range of input and output devices designed to provide a rich user experience. The buttons and chess clock allow players to interact with the board, while the small touchscreen display provides a user-friendly interface for accessing different features and settings. The chessboard itself is equipped with 64 squares, each with its own magnet sensor to detect the presence and movement of the chess pieces. The addressable RGB LEDs are placed beneath the playing surface of the chessboard, allowing them to light up to indicate possible legal moves for the pieces that have been lifted off the board. To enable the microcontroller to detect the position of each piece on the board, I/O expanders are used. These provide sensor output to the microcontroller, allowing it to track the position of all playing pieces using only 2 wires. The final result is a beautifully crafted 3D rendered model of the fully assembled board. Every component has been carefully placed and connected to ensure optimal performance and functionality, making this board a must-have for any chess enthusiast looking to take their game to the next level. After receiving the fabricated board, we encountered several design problems during testing. The first issue was with programming the microprocessor. The ESP32 has strapping pins that have a unique behavior during boot time, and one of the pins must be held low for the programmer to upload the firmware to the microcontroller. However, the original schematic design showed that the pin was connected to the logic level shifter, which is held high, making it impossible to program the firmware. To work around this problem, we had to scratch off the trace to that pin, which unfortunately rendered the addressable RGB LEDs useless. Realizing that a redesign was necessary to address this issue, we opted to split the board into 2 separate ones, one for the controller and another for the chessboard. The 2 boards are connected together using a flexible flat cable. Although this solution required additional time and effort, it was much cheaper than fabricating an entirely new board. This also allowed us to improve the design of each board, making them more compact and efficient in their respective functions. After sending in the production files to the fab house for the second iteration, we were pleased with the improvements made to the design. However, we encountered 2 issues during testing. The first issue centered around the addressable RGB LEDs, as the first square would randomly flicker each time an update was sent through the data line. After investigating, we discovered the issue was due to crosstalk on the flexible flat cable, which was interfering with the signal integrity. This issue was not unique to our design, and we found that other projects had also experienced similar difficulties. One potential solution we came across was to alternate the ground with signal lines across each pin in the flexible flat cable connecting the chessboard and the controller. Another problem that was discovered with the second iteration design was the interrupt pin assigned to the Hall sensors. The interrupt pin was connected to an input pin on the S32, but it did not have an internal pull-up resistor. This meant that the microcontroller was unable to receive any interrupt signals from the I/O expanders. To address this issue, we combined 4 interrupt pins into one pin and reassigned to a different pin on the microcontroller to ensure that the interrupt signal was properly received by the microcontroller. Despite these setbacks, we were able to successfully overcome these design problems and create a fully functional chessboard with a combined controller. Adjustments were made to the third iteration of the design to implement the changes identified in the previous iteration and refabricated the boards. Before fabrication, we switched to the ESP32 rover module, which has 8 megabytes of RAM compared to the original W-Room module's 4 megabytes. This was necessary as the firmware code was too large to fit on the original module's working memory space for MicroPython to execute the code. Fortunately, after testing the new boards, we found that the flickering issue in the first square had been resolved and the interrupt signals from I/O expanders were working as expected. While this issue added some extra time and effort to the project, we learned valuable lessons about signal integrity and design optimization. Although we still had an issue with random LEDs flickering all over the board, We suspected that part of the board design may have been acting as an antenna, capturing radio signals that were interfering with the signal integrity. While we did not experience any issues with I2C communication, we recognized the need to optimize the design further to reduce noise on the data line. Overall, while these issues added extra time and effort to the project, we recognize the valuable lessons learned about signal integrity and design optimization. We are continuing to investigate ways to improve the chessboard PCB designed to reduce noise and ensure optimal performance. With the PCB design issues sorted out, it was time to turn our attention to the software side of the project. We chose MicroPython as the programming language for the ESP32 microcontroller since it is lightweight, easy to learn, and has good support for hardware interfacing. One of the key challenges was designing the user interface for the chess game. We wanted a modern, intuitive interface that would make it easy for players to interact with the game. To achieve this, we decided to use a next-gen touchscreen display. This allowed us to create a custom user interface with buttons, icons, and text that was tailored to the needs of the chess game. Under the hood, the chess game logic was implemented, using a technique called bitboards. Bitboards are a way of representing the current state of the chessboard, using binary numbers. Each square on the board is represented by a bit in a 64-bit number. A 1 indicates that a piece is present on that square, while a 0 indicates that it is empty. By using bitboards, we were able to perform fast, efficient operations on the board state, such as checking for valid moves. One of the key challenges with implementing the bitboard approach was detecting changes to the board state. We accomplished this by using two bitboards, one representing the current state of the board and one representing the previous state. Whenever a player lifted a piece off the board or placed one down, the two bitboards would be XORed together. This would reveal the position of the piece that had been moved, allowing the game logic to update the board state accordingly. Overall, the combination of the bitboard approach and the next-gen touch screen display allowed us to create a chess game that was not only highly functional, but also had a modern, user-friendly interface. In conclusion, this chessboard project was a challenging yet rewarding experience. We faced many design and software issues along the way, but we persevered and ultimately created a functioning and aesthetically pleasing chessboard. We learned valuable lessons about PCB design, signal integrity, and software optimization. We also had the opportunity to explore the capabilities of MicroPython and the next-gen touchscreen display for the GUI. Overall, this project was a great example of how interdisciplinary skills can come together to create something amazing. We hope to take the lessons learned and apply them to future projects, and we are excited to see where this project will take us next.